Okay, today I'd like to summarize the ideas that have come out of the chaos game and the Sierpinski Triangle. Um, Video is going to be a little bit long, but it's about all you're going to have to do today is listen to this, watch this video, so bear with me. We start with triangle ABC. I've made it an isosceles right triangle because it makes it easy to draw the inside regions. And I'm on graph paper, so a right triangle's good. You'll often see an equilateral triangle online when you look at examples of the Sierpinski triangle. The truth is, you can have a triangle of any sort be the Sierpinski triangle. So I'm working with an isosceles right triangle. The way it goes is, suppose in the chaos game we start at point A, and then we go halfway to B, and then we play around with A's and B's and A's and B's for a little while. So then the entire time so far, we're on segment AB. At some point, we're on segment AB and we roll our first C. The probability of not doing that is vanishingly small, so we'll assume that's what happens. Then at that point, we go from wherever we are on segment AB halfway to point C. And the fact is, and this was, I think, giving some of you guys trouble, when we do that, we will land on the mid-segment A1, B1, the one that's half as long as segment AB and parallel to AB. We will land on that mid-segment. So let's say I'm here, I go halfway, I will land there. Some of you guys were troubled by, do we get all the way there? We're only going halfway. The truth is we never really land in the interior of any of these excluded regions. We always land on their boundary. We always land on the triangles themselves, not in the interior of the triangle. So our first move is to the mid-segment A1, B1. Then we start going to the A's and B's and C's and the A's and B's and C's. What happens is this region is empty precisely because the only way to land in this region is to come from somewhere outside the triangle, go halfway to one of those 3 points. But because we never are outside the triangle, we can never land in here. Then we see that the only way to land in these sort of next size down empty regions, which I've colored, what's this called? It's called something, I don't know, it's green. The only way to land in these is to have been in triangle A1, B1, C1 and go halfway to A or B or C. So if I'm here and I go halfway to A, you can see I land in here somewhere. In fact, this is kind of cool. Where I land is at some point in this triangle, which is proportionally similar to the point I came from. But because I can never be in this triangle, I can never land in any of these 3 green triangles. Because I can never land in any of these 3 green triangles, I can never land in any of these orangish triangles, etc., etc. So the emptiness of the topmost region forces the emptiness of the next regions down, and the next regions down, and the next regions down. So there's the Sierpinski triangle, which is the result of the chaos game. The question then becomes, how much of this triangle, how much of triangle ABC is in fact empty? To do this, let's start by supposing the area of triangle ABC is 1, or 100% if you like. It should be clear, then, that the area of triangle A1, B1, C1 is 1/4 the area of the large triangle. So it has area 1/4. Then the question becomes, what's the area of the next set of empty regions? Count them. There are 3 of them. And each one is 1/4 of 1/4 of the original triangle. So they're each 3/16 of the original triangle. Actually, I'm not crazy about that green. don't know if you can see that or not, guys. Now what's the area of the reddish-orange empty regions? Again, let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 empty regions. The next size down. And how big is each one? Well, that triangle you're looking at right there is 1/4 of this triangle, which is 1/4 of this triangle, which is 1/4 of the original triangle. 4 of a 4th of a 4th, that's a 64th. So the 9 red regions are each 1/64th of the entire triangle. So in sum, they constitute 9/64ths of the original triangle, or in total area. Then we come to the next size down, which I've only covered one of, but it's black here. How big is it? How many of them are there? Well, there's a pattern. Every time we look into an excluded region, they are a 4th as big as the last ones. This triangle is a 4th of this, which is a 4th of this, which is a 4th of this, which is a 4th of the entire triangle. 4 times 4 is 16. 16 times 16 is 256. So this triangle is 1/256th of the entire triangle. How many of these are there? Again, there's a pattern. There's 1, 2, 3 here, 1, 2, 3 here, 1, 2, 3 here. 3, 6, 9, 9, 18, 27. There are 27 of these triangles. Each is a 256th of the entire triangle. And therefore, in total, those regions constitute 27 256, which you look at it is about a 1/10 of the entire triangle. Next size down. Well, I don't have any of the next size down drawn, but if you like, I could say, you know, look at this triangle right here. How many of them could I draw? Well, I could draw 256 times 4 of them, and each would be, sorry, I did that backwards. I could draw 27 times 3 is 81 of them, and each one of them would be 256 times 4, 1,024th of the entire thing. The pattern is times 3/4, times 3/4, times 3/4, times 3/4, etc., etc., etc. The question now becomes, what does this infinite list of fractions add up to? What has happened is we started with the chaos game. It gave us the Sierpinski Triangle, and the Sierpinski Triangle gave us this infinite summation. The chaos game has led us into 2 areas of math which are going to be related, but which we're going to study separately for a time. The first is infinite sequences and sums, which is what we have here. And the second, which some of you have already anticipated, I'm sure, is fractals. The Sierpinski Triangle is a fractal. What is a fractal? Well, here's what's going to happen. Today, I simply want you to watch the video, and that'll be enough for me. Tomorrow, Mr. Hinders and I are going to send out a little survey just to kind of ask you guys how things have been going. Next week, in the week before Easter, we're going to spend some time with infinite sequences and series. I promise we're going to come back to fractals. We're going to loop back to fractals after Easter. Tuesday after Easter. We'll come back and we'll talk more about fractals. But if you want to kind of know where things are headed, we're headed in 2 different directions, which are related and which are going to have things to do with each other, going to inform each other. But that's where we're headed starting sort of today, sort of Monday. I'll send out a survey tomorrow morning just to see how things are going. And other than that, until then, stay safe, stay clean, stay home. Bye-bye.